All right, here are some of the wave functions for the simple harmonic oscillator. This is the wave function psi naught for the 0-point energy wave function. And so we'll notice then that there's a maximum probability of finding the particle at the equilibrium position. Okay, whereas in a regular simple harmonic oscillator, you might think of the maximum probability as more likely being near the ends, because it's moving fastest in the middle and slowest near the ends. So here we're seeing that if this were psi squared, then it would peak out when it's at the equilibrium position, be more likely to be found there, even though in a classical problem we would see it as spending more time in the areas where it's moving slower, which would be near the endpoints. But let's start to progress upward through these different Hermite polynomials. Here's the psi2 function. Here's the psi1 function. Okay, so these are just those Hermite polynomials that I showed you before. This is the psi3 function. If we keep going, there's psi2 squared, psi1 squared, psi3 squared. So that's our probability density. Notice what's starting to happen though. As we go to higher values of n, we start getting more probability of finding it where we would classically expect it to be, which is out near the edges, because that's where it's moving slower. So therefore it should be spending more time there. And if you make a lot of measurements of it, it would have a higher probability of being found in areas where it's moving more slowly. So it's starting to correspond to a classical problem. And here, this is psi10 squared. Okay? And so we see here that this is starting to follow more the path of the u function, in which it has a higher probability of being found out near the edges and a minimum probability of being found near this middle point. Okay, so what I'd like to do from here is move ahead, and in your Canvas website, you're going to find atom 3. And atom 3 is where I'm going to put the solutions for the hydrogen atom. And so that's where I'd like to go next. Now here, what we have is a more physically realistic problem, in that we are looking at the solution to the Schrodinger equation for a spherically symmetric potential energy function. And so whereas before we had this kind of an equation, minus h bar squared over 2m d squared psi dx squared plus u psi equals e psi. This is just 1D. But if we have a three-dimensional problem, then we have to take into account the variations in psi with respect to y and z. So if psi is a function of x, y, and z, then this second dimensional operator turns into a gradient function. This becomes minus h bar squared over 2m times the partial square root of psi with respect to x squared plus the partial square root of psi with respect to y squared plus the partial square root of psi with respect to z squared plus u of psi. Now the potential energy function for an electron going around the hydrogen atom, u here is just minus 1 over 4 pi epsilon naught e squared over r, where r is our spherical coordinates radius. And so we could write that then as minus 1 over 4 pi epsilon naught e squared divided by the square root of x squared plus y squared plus z squared. And so that's going to go in here for u of psi. Okay, so this will be minus 1 over 4 pi epsilon naught e squared divided by the square root of x squared plus y squared plus z squared. And then that will equal, on the right-hand side of this equation, e of psi. So this is our task then with the hydrogen atom solution. Is to rewrite a second derivative, and this can be written as a del squared operator, for those of you that have had this kind of vector algebra. But here we can just see that it is essentially taking the derivative of psi twice with respect to x, y, and z, while keeping the other constants, the other variables a constant for differentiation with respect to that variable. Okay, and so this is the correct version of the Schrödinger equation for the hydrogen atom in Cartesian coordinates. The problem, though, is the square root factor. The square root factor, it makes it impossible for you to separate this out into functions that are strictly in terms of x, y, and z as product functions. It's impossible to factor this properly in order to get the sort of solution that we're looking for. And so instead, it turns out to be more natural to use spherical coordinates to solve this problem. So if we use spherical coordinates, then we are able to write the potential energy function just as e squared over r. And so that turns out to be a more natural coordinate system to use for this problem. And so this is what we see here then, is the rewriting of our Schrödinger equation requires that we write x, y, and z as a function of r, theta, and phi. And then we solve that equation in spherical coordinates.